how much air resistance do we have on car or different objects, as well as on the airplane. And then we are going to cover turbomachinery. We are going to cover the turbomachinery, which will be the last part of the fluid mechanics for this semester. In turbomachinery, we will cover the pumps, turbines, and then the rotating equipment. Okay, this is generally called the rotating equipment. And this is the roadmap for our semester. And then we will have also the lab sessions. Okay, the lab sessions will be done by Nasimi. Okay, so he will be your lab session instructor. So for the lab sessions, we have again the same fundamental concepts. We'll also have the lab session. Here you will see the viscosity, fluid friction. Viscosity, we mean fluid friction. You will see the Archimedes principle, and then surface tension, the fundamental concepts in fluid mechanics. And then in the next lab session, you will see the hydrostatic pressure, the rho GH that you have seen in high school, but now it will be more detailed. You will have the different derivations. We will see in today's lecture. And then horizontal Reynolds number demonstrator. This will be your next lab session. In that lab session, you will see different regimes of fluid flow. Then fluid flows, you will have different regimes on molecular viewpoint. Sometimes it can be chaotic, or sometimes it can be very ordered. Okay. And then flow visualization will be your next lab session. In flow visualization, you will see how we visualize the flow of water and the air. We are using different methods because water and the air are transparent. You can't see what happens inside the system. Therefore, we use different methods to see the trajectory of the fluid particles. Therefore, this will be your next lab session. And then we will talk about the Bernoulli's principle, the famous principle that you know from high school, and head losses in pipeline systems. You can say losses in pipeline systems, because this is also important. At the end, you will have to buy some pump, and in this, as a result of knowing the losses of the pipeline system, you can know how much pump is required to deliver the fluid from one location to another location. If you have a building system, for example, what power of pump is required for it can be clean water system, or it can be sewage system. Okay. In all of the cases, you are going to, in sewage systems, we don't need pumps. Okay, this is for the cleaning system, but for the head losses, we are also covering the sewage system. And then aerodynamic unit. So in this unit, you will see the aerodynamic effects of airflow, like the drag resistance, air resistance. Here you will see, and also the application of the energy conservation and the mass conservation on the air. Okay, this will be the next lab session. And another lab session will be on the turbines. These two turbines are used to produce electricity. Okay, these are very famous turbines. And in any in any water electric station, you can see these two turbines, Pelton turbine or Francis turbine. These are very famous, even in Azerbaijan or any country of the world. And this will be the lab sessions and for this semester. Okay. And also the inevitable part of our lecture will be the homeworks. Okay. You will have homeworks for the fluid mechanics. But these homeworks, all of the homeworks will be covered in groups. Okay, you will not have the homework for the whole classroom, but I will divide the classroom into groups. It can be 5 groups or 6 groups, and each group we will have different numbers and different values, as well as different questions, so that there is no any cheating in the classroom. And you can expect up to 5 homeworks. It can be more. At the end, this is the planning for the semester. We hope that we can finish all of the chapters and all of the lab sessions as well as homeworks, but it is planning. Okay, as I said, it is planning. There can be more or less, but we are hoping to finish all of them. And this is about me. If you are interested, you can read it by yourself. Okay, then the roadmap for today. And for the roadmap of today, I will first talk about some fundamental concepts in fluid mechanics, because these concepts are building blocks of fluid mechanics. So you are building the other laws of the fluid mechanics on these fundamental basic concepts. And then I will talk about the Newton's law of viscosity, and this is also a very important building block of the fluid mechanics. It comes from the 17th century, okay, 17th century, but it is 3 centuries older, but it is used, it is main part of the cornerstone of the fluid mechanics. And then comes the last topic for today, which will be the hydrostatic force on submerged surfaces. And for this one is also important for your lab session as well as the application. This is the application. This is also important for your lab sessions. Okay. And I can say that the first topic is easy. So here, the illustrations, there are a lot of illustrations, photos, and videos, so it can be funny for you. But the next topic, it is hard. But the last topic is hardest, because here you will have the differential equations. For the sum of the fluid mechanics, we will need differential equations. Okay, we will have sometimes. Therefore, be prepared that you will see mathematics in some part of the fluid mechanics. Okay. And this is the roadmap for today. And we are starting from the first part, which is the concepts in fluid mechanics. And firstly, what is mechanics? Then we can talk about what is fluid mechanics. The mechanics from Cambridge Dictionary, this is the definition of the mechanics. It studies effect of the forces. So Mir Mevsim is too late. Mir Mevsim, next time, please be on time. Okay, this is the definition of the mechanics. It studies the effect of forces on objects and their movement. Okay. In other words, mechanics studies interactions between forces and the objects. And sometimes the objects can move. When it moves, you are studying the dynamics. Sometimes the objects are not moving in statics. Okay. They are in equilibrium. If objects are in equilibrium, if they are not moving, there is no any net force. So therefore, this will be the statics part. And if the objects are moving, and we are learning the dynamics part, this one is a bit more difficult than the statics part. And this is the definition of the mechanics, the interaction between forces and the objects. And then another name for mechanics is the continuum mechanics. You will see the meaning of continuum in our next slides. And mechanics is divided into 2 parts. One is the fluid mechanics, the other one is the solid mechanics. And in solid mechanics, as a part of it, you see also the mechanics of materials, or strength of materials. Okay. The strength of materials, it is under the topic of the solid mechanics. And for the fluid mechanics, we have the 2 groups as a classification. One is fluid statics, and the other one is the fluid dynamics. In fluid statics, the fluid doesn't move. The name says it. Okay, it doesn't move. There is no any net force on the fluid. For the dynamics, the fluid moves. There are forces acting on it. For kinematic part of the fluid dynamics, this one is also divided into 2 parts, kinematics and kinetics. For kinematics of the fluid dynamics, we are looking at the geometric picture of the motion. Okay, geometric picture of motion. And we are seeing here the velocity, acceleration. Okay, so some geometry. We are analyzing geometry, angles, the location, and the change in locations. Okay, it is only geometry. But in kinetics part, you are analyzing the forces. Okay, forces with motion, the real picture. Okay, here you see the real picture, and here you see the geometric picture. And then the kinematics is divided into 3 parts, which is the ideal fluids. And for ideal fluids, we have, ideal means no friction. Okay. Why do we use ideal fluids? Because sometimes friction is very, very small. Therefore, it is very approximate model to understand the flow. And sometimes it is simple, because ideal fluids do not have a very complex governing equations. Therefore, it is very easy to analyze ideal fluids. And we have the viscous fluids. For viscous fluids, this is the real part of the world where we live. Okay, this one is the real. And it is very complex. And in some part of our lecture, most part of our lecture, we will use the viscous fluids for analysis. And then comes the compressible fluids. And the compressible fluids are, the name says it, okay? The compressible means the fluid that can be compressed. It is very easy. So the easy definition. So For example, let's look at the difference between water and the air. Okay, when you try to squeeze or press the water is not compressed. Okay, because it is incompressible. The name says it. But the air, when you try to squeeze or press the air with your hands, for example, air balloon. If you have the air balloon, if you try to press it, it will be compressed. It will change its size. But here, you cannot change the size of the water. If you have a bottle of water, you cannot change the size of the water inside that bottle. It will be constant. But for the air balloon, you can change the size of the air balloon, and then you will have the compression. In other words, when we say compressible, it means that size can change. For water, for example, if you apply 20 megapascals of pressure, 20 megapascals, here you will have less than 1% volume change, less than 1%. So it means that it is very incompressible fluid. And this is the last part of the kinematics, and here we are covering, I've said here, drag and the lift or aerodynamic part. This is the compressible flow. These two are about the compressible flow. The rest is about incompressible flow. Okay, now comes the concept of continuum. Here we have said that mechanics is also called the continuum mechanics, and why do we call it continuum mechanics? Let's see it. So I will have two examples here for you to understand the concept of continuum. And by the way, continuum, this one is historical. Okay, historical. Because you will see why it is historical in my next explanation. But firstly, what is continuum? Let's understand it. We have two examples here. One is the glass of water. The size of the glass of water is 160 cc. Cc means cubic centimeters. And the size of the air is 1 cc, 1 cubic centimeters. In 1 cubic centimeter of water, we have 3.3 10 to the 22 molecules. Okay. Therefore, one glass of water, it will be 160 multiplied with this quantity, and you will get this amount of molecules. Okay. In a similar manner, 1 cc of air will contain less molecules because from molecular point of view, air contains less molecule per 1 mole. And therefore, you will have this amount of molecules in air, in 1 cc of air. So what does this picture tell us? This picture tells us that if you are trying to understand the motion of flow, for example, if you are trying to understand what happens inside this glass of water from molecular point of view, it is very difficult. Okay, let me write it. Molecular view analysis is difficult. Okay, because there are lots of interactions, 10 to the 22 molecules, they are interacting with each other. For example, one collision, if you take the collision time, so one molecule comes here, another molecule comes here, they are collided with each other. It happens 10 to the power of negative 9 seconds. Okay, it is very short time. But if you take all of these molecules and if you try to understand what happens in 1 second, you can see a huge number. Okay. For example, if say that this is very difficult to analyze by pencil and paper, if you use computer, okay, and let's assume that your computer is very super computer, and then you will need millions of years. Okay, you will need millions of years to understand what happens in this macroscopic view. This one is the macroscopic view. Okay, macroscopic view, and the molecular viewpoint is microscopic view. And if you are trying to understand what happens in this macroscopic view, for example, what is the pressure here? What is the temperature here? Okay, what is the density here? If you are trying to get these quantities from molecular point of view, it is very difficult. Okay? And I said, even with supercomputers, you will need millions of years. And then comes the historical approach, which is continuum approach. Why it is historical? Because when the people started to analyze fluid flow or the solid mechanics, there was no any molecular, so the people didn't have any knowledge of the molecules. They didn't have any knowledge of the molecules. They were thinking that any material, this one fluid or solid, it is continuous. It doesn't have any molecules with some empty space. Okay, there is empty space between any two molecules, but the people in the past didn't know that there are molecules, there are empty spaces between them. They were always thinking that there is not any empty space and the material is continuous in its all of the locations. Okay, therefore it is the continuous historical approach. And then it comes the definition of the concept of the continuum, and it says that where we say fluid properties from macroscopic point of view, we are analyzing from macroscopic point of view, and we say that the matter doesn't have any empty space. Okay. So it is, now comes the other example from concept of the continuum. If it is, why it is true and why it gives exact results. Okay. So firstly, we will say that you have a glass of water. So this one is glass. So inside that glass, you have water. Okay, this is the water inside that glass. And you are taking a small volume here. So you take this small volume, dV, differential volume. It is calculus dV, or you can say that delta V. Okay, this small volume is on the size of 10 to the negative 20 centimeters cube. This is the size of this small elemental volume. And I zoom it, and you will see something like this one. And this volume, the delta V or dV, that you have taken for analysis is so small that the molecules can be comparable. Okay, you have one molecule here, you have another molecule here. Okay, and this part is empty. There is no any molecule here. And we are trying to understand what is the density of this small volume. And I know that density is this one, sum of the masses divided by the volume. And in this case, volume is dV, and the sum of the masses is the mass of this atom, m1, and the mass of this atom, which is m2. Okay. m1 plus m2 divided by this volume, it will give me the density. But the problem here is that these are the molecules inside the system, but the system is very small. As it is very small, it is possible that one molecule comes inside that system. And it's also possible another molecule leaves the system. It is also possible two more molecules comes into that system. You can see the volume is constant, dV is constant, but the mass inside the system changes. It changes with time. Therefore, what you are saying here is that as you increase, here you have the variation of the density. You don't have one fixed amount of density, but this density changes because some molecule comes, some molecule leaves. Therefore, the mass inside that constant system changes. Therefore, you have the changing amount of this density. But after some point, say that this volume, till that volume, you have the constant amount of the density. In other words, when we say that density of water is 1000, okay, and this is the place that we are talking about. You go into smaller dimensions, you will not have any fixed amount of density due to molecular view. If you go to larger size, again, you will not have the constant amount of density because in some parts of the system, you will have high density, in some parts, low density. Okay, at the end, when we say that fluid mechanics, when we say that solid mechanics, when we say that strength of materials, we are talking about this part of the view, which is the continuum part. Okay, and why when continuum analysis is valid? It is valid if this Knudsen number is much smaller than 0.01. Okay, Knudsen number is the lambda, which is the distance between molecules divided by the length of your system scale. In this case, if this is my system, the length of my system is L, and the distance between any two molecules, this molecule and that molecule, is lambda. If this lambda by L, this ratio is much smaller than 0.01, then we can say that continuum approximation is valid. Otherwise, you will have to use some statistical approach, because if you are in molecular view, you have to use statistical approach. And if you are in this part of the view, you have to use, again, statistical approach. But in this case, you can use the famous laws of mathematics, calculus, derivatives, integrals. Okay. And this is the first concept. Another concept is what are the forces acting on a fluid body? And say that this is your car that moves in that direction. Okay. And I take a small area here on that car, a small area, and say that this is the force that is acted by air. This is acted by air on my car. Okay. This is the resistance or friction. Okay. And what I do is that, if you know from mechanics of materials, I divide that force into two parts. One is the tangential or shear force. This one is the shear. Another one is the normal force. Okay. Shear force is tangential or parallel to the surface. This one is the parallel to the surface. And I also have the normal part. The normal part is the normal to the surface. Okay. Therefore, we will have the two components. One component is the tangential to the surface. Another one is the normal to the surface. And in fluid mechanics, when we say the normal force, it means that most of the time pressure. Okay. And when we say that shear force, and it means that most of the time friction. Okay. And that is the term that you know from the dynamics or the solid mechanics course. And then another classification of the forces is that they are divided into two parts. One is the body force, and the other one is the surface force. Okay. When we mean body force, it says that it acts overall body, okay, throughout the body of the system. Therefore, it is called the body force. Example is the gravitational force, magnetic, electromagnetic force. For example, you cannot say that my hands feels the body force, but my legs doesn't feel. The gravity affects overall of your body. Okay, the gravity G is present in every location of your body. Okay? Therefore, the gravitational force or electromagnetic force, radiation, affects all of your body, all of the points inside your body. Therefore, we are calling these body forces. And another force is the surface force. And these surface forces are acting only at the surface of the material. For example, the pressure. So if the pressure acts only at the contact. So this one is the contact surface. Or the shear force. If you have shear force, say this is your material, there is shear force acting on that material. This one is the F, shear. Okay, that shear force only acts at the contact surface between the material and this application. So here you have the contact surface. And therefore, this is called the surface forces. And body forces, these forces are proportional to volume because it acts on all points of the body, but the surface forces are proportional to the area. Or body forces are proportional to mass. For example, gravitational force, which is mg. Okay. But the surface forces are proportional to the overall surface area of the material. Now comes the definition of the stress, another concept in fluid mechanics. The definition of the stress is that we have two types of stresses. One is the normal stress, this one is the normal, and the tau is the shear stress. And normal stress is, we have said, you have the normal force. That normal force divided by area, so this one is yours, delta A. Delta means small area, okay? That force divided by the area, but the normal force here we are talking about, but this normal force should tend to 0. You can see the limit definition here. It should tend to 0. Why? Because when delta A, this is the area, when it tends to 0, then this area becomes point. Okay. Therefore, we are saying that normal stress at point P, it means that the normal component of force dF, but when the delta A tends to 0. That is the definition of the normal stress. Similar definition for the shear stress. It applies to the area when the area tends to 0. and it is the division of the shear force over the differential area. And now comes the main part of our lecture. The main part is the difference between fluid versus solid. Okay, that is, what is the difference between fluid and the solid? There are different definitions, but we can say that the molecular view of the fluids are different than the molecular view of the solids. For example, the molecules of the solids are more compact than the molecules of the fluids, which are scattered. But the definition that we are using in fluid mechanics or the mechanics is that the fluid deforms under the applied shear stress. It deforms continuously. For example, this is bread, and you are trying to spread the butter on your bread. Okay, you are trying to spread it. But you can see that when you are trying to spread it, it deforms continuously. Okay, it doesn't have any fracture, it doesn't have any break, it deforms continuously. The famous word that we are using, the water, for example, is that it takes the shape of the body. It takes the shape of the body. Why it takes the shape of the body? Because it deforms continuously under applied shear stress. That is the definition for the fluids that we are using. But for the solids, the definition is different, because solids resist applied shear stress till some point and then they break. The famous example I can give you is that the scissors. Okay, scissors are working by the shear stress, because you have two blades of the scissors. This is the blade 1, and this is another blade. This is blade of the scissors, and there is a small gap here. That small gap allows you to apply the force by the shear stress, by the tangential stress of the scissors. And if you are trying to apply this tangential stress, for example, for the paper, you cut the paper. Okay? Paper resists till some point, but then it breaks. Okay, for the fluids, this deformation doesn't happen. The fluid deforms, this type of deformation doesn't happen. Fluid deforms continuously. It doesn't break. For example, the famous butter and the bread example. Okay, so this one is so you have, now we've come to another example. Let me tell you, this one is the knife. Okay, this one is the bread, and inside that system you have this butter. Okay, butter is fluid. And when we say fluid, it doesn't mean it is liquid. For example, it can be liquid, it can be air, it can be blood. Blood is also fluid. It can be honey. Honey is also fluid. Okay. It can be even asphalt. Okay. Okay. Asphalt is also fluid. There are different types of the fluids. When we say fluid, it doesn't mean that it is water. Okay. Water is also included in this example. You can oil, for example. Some ranging different example as toothpaste. Okay, this toothpaste is also fluid. Paste, it is also fluid. So when we say fluid, it doesn't mean that it is liquid or air. It's different range of the fluid. In this case, we are looking for yes.
Asphalt, it's fluid?
Yes, asphalt is fluid. Yes.
Why have possibly?
Yes, asphalt is fluid, but it is the. So we'll talk about this one in our next slides, but asphalt is a kind of fluid.
Okay, teacher, okay.
So these are the types of the fluids, and it can be other fluids too. You will see in our next slides. Okay, now what happens when you apply shear stress on this butter? Okay, so at the beginning, when you don't apply it, the molecules of the butter are one location, are in one line. Okay. The molecules are in one line. But when you move the knife in that direction, what will happen is that these molecules comes forward, and this molecule also comes forward, this molecule comes forward, this one also comes forward. But the molecule here is stationary. Okay, I say molecule, it is not molecule, it is particle. Okay, in fluid mechanics, I've said we are talking about particle. This particle moves forward, this particle moves, but this one is stationary. I will say why it is stationary. You move forward again, molecule comes here. Say that the knife has a velocity of v. If it has the velocity of the v, the molecule here also will have the velocity of the v. But the molecule here is stationary. V is 0 because this plate doesn't move. The reason I will tell you in next slides. Okay, again, molecule moves. Okay, that is what happens when you apply the shear stress on butter on the bread. Okay. Now comes the reason why we have the velocity v here and why we have the 0 velocity at the bread part. Okay, let's see one experiment here. But this is the experiment. So this one is ink. This is the ink, and they are injecting dye. Ink, the dye, I mean the ink, into the system. You can see this part moves, but this part doesn't move. You can see it is stationary, doesn't move. You can see it cleans, then it moves. But this part moves, this part is stationary. And that is what we call as the no-slip condition. Let me write it here. No slip boundary condition. No slip. Okay, slip means no slip boundary condition. So what it means is that the fluid takes the velocity. Fluid takes the velocity of solid boundary. So I can give you different examples, but let me take you 2 or 3 simple examples. So one example I can give you is that, say that this is pipeline, okay? Inside that pipeline, water moves. This one is water, and this is your pipe, okay? When water moves, in that pipeline, we have solid boundary. Where is that? Solid boundary is here, and the solid boundary is here. The velocity of water at this solid boundary is 0. V is 0, and the V is 0. Water at the boundary doesn't move. So you can say that there is one layer of water inside the pipeline that is always there. Okay? It doesn't move forward, it doesn't move backwards, it is always there. That's at the location of the solid boundary, okay, where it touches solid boundary. This can be one example. I can give you another example. So I have said it here. You move the knife in that direction with velocity of v, okay, and the butter molecules or particles take the velocity of v at the boundary. These are v, but this one is another boundary, which is the bread, solid boundary. When we say boundary, we mean solid. And here the velocity of the fluid particles are 0. Okay, so here fluid particles don't move because the solid boundary doesn't move, and here fluid particles moves because the knife moves with velocity of v. This is the no slip boundary condition. Let me give you one more example and finish. So one more example, it can be that, let's say this is the ground and wind blows over the ground. This is the wind, okay? And we know that ground doesn't move. And I've never seen this one till now, okay? Ground is stationary, always it is stationary. So it means that the wind molecules or wind particles at the ground, this part has 0 velocity. Velocity is 0. Okay? You can increase the number of the examples. At the end, the statement is that when you have the fluid and the fluid is at the boundary with solid border, when the fluid has a border with solid, for example, here. Here you see fluid has a boundary with the solid at the surface of the car. Along this all location, you have the velocity as 0. Okay, no slip boundary condition. We can increase the number of examples. There are lots of millions of examples, but this is the essence of the no slip boundary condition. Now comes the Newton's law of viscosity, and I think with this one we will finish today's lecture. And the Newton's law of viscosity is very important in fluid mechanics. So what is Newton's law of viscosity? So it is very similar to Hooke's law. Okay, what does Hooke's law says? Hooke's law says that force is proportional to displacement, x. So if you have spring, okay, and spring is suspended from some surface and you are applying some force F. Okay. This spring will deform with the amount of del x. Okay? And that del F is proportional to that del x with some coefficient of k. This is the Hooke's law. Same, not same, but similar. Similar relationship holds for fluids. But in this case, we don't have this tension or compression force. In fluids, we have F shear force. Okay, that shear force is proportional to, with some coefficient of C1, to the deformation of fluid. Okay, in solids, deformation shows itself as del x. Okay, when we say solids, we are talking about del x. But for fluids, as I said in our previous slide, it deforms continuously. Okay, for fluids, we don't have one constant amount of del x under applied force because del x increases continuously. Here we are talking about deformation, not deformation, but rate of deformation. Okay, rate of deformation. What is rate of deformation? That is how del x changes with respect to time. Because it deforms continuously. Fluid deforms continuously. If you apply force, it deforms. If you apply force, it deforms. Okay, when you stop force, it doesn't deform. Therefore, here we are talking about the rate of deformation. How deformation changes with respect to time. That is proportional to shear force. But for the solid materials, you say that we apply the force, the material deforms, solid material deforms with some fixed amount of del x, and that is proportional with some coefficient of the k. That is the main difference between fluids and the solids. Now comes the Newton's law of the viscosity. So we will draw the Newton's law of viscosity for today's lecture. So what it tells is that, say that we have two plates. One plate is here, plate 1. Okay. Another plate is here, plate 2. I'm saying plate, you can understand this one as pipeline. For example, pipe. This one is the top part of the pipe, and this one is the bottom part of the pipe. Okay. Or you can understand this one as knife and butter. Okay. This one is the knife that moves, and this one is the bread that is stationary. At the end, we are trying to understand what is the response of the fluid under the applied force. In solids, we know it is Hooke's law. But in fluids, what is the response of the fluid to the applied force? To understand this one, the Newton used 300 centuries ago, he used this example. And he says that the plates are in a distance of L. There is a distance of L between these two plates. And before starting the experiment, he says that the particles are in one location. These are the location of the particles. And then he starts to pull the top plate with velocity of v and with the force of F shear. It is constant shear force. It starts to move this shear force. What happens is that, as I said in our previous example, the fluid molecules moves to a new location here. But the molecule here doesn't move because this plate is stationary. Okay. And after some time of this one is time is 0. Okay. This one is time is delta t or dt, let's say. After small time. After small time, there is an angle change. This is d beta. Okay, the angle is d beta. The angle change between these two lines. Okay, and the time is dt. And this fluid here, fluid particle here, this particle moves a distance of velocity into time dt. Because I said, due to no solid boundary condition, the particle takes the velocity of the solid boundary. Here, solid boundary moves with velocity v, therefore particle will have the velocity v. And here, solid particle doesn't move, therefore you have the 0 velocity. And that is the essence of the Newton's experiment to understand what happens inside the fluid. So he says that now with similar approach to Hooke's law, and then with Hooke's law, he says that tau is F by A. Instead of taking the shear force, he takes shear force by area, which is shear stress. And he knows that the velocity changes linearly from this location to that location. It is linear change. Okay, and that linear change will be equal to y by L distance. Y is that coordinate into v. V is the velocity here. Okay, because when you put y as 0 location here, you can see u is 0, u velocity is 0. And when you put y as L, the L here, and the velocity is v itself. Okay. And then he takes the derivative of u with respect to y. That's the derivative of u with respect to y. It makes v by L, because that is the formula, and this one is very simple derivative. So you take the derivative with respect to y, it will be v by L. And what is u? U is the velocity of the particles. Particles moves in that direction. This moves in that direction. Okay, particles moves in that direction. The velocity of the particle has u. Okay. U is velocity of particles in x direction. Okay, and the distance between these two plates is L. And here velocity is v, and here the plate doesn't move, u is 0. And then he says that dA is v dt. I have said this one. This is the dA, and that dA is v dt. Okay, and the angle, I've said this one. This one is the angle that changed the beta after time of dt. The angle of the tangent of the angle is the same of the angle itself, because it is very small. At very small angles, you can say that tangents of the angle is same as itself, or if it is sine of the d beta is same as d beta itself. And that one is equal to tangent of this angle is the dA, the opposite side, divided by L. L is this one, which is the adjacent side. Okay, opposite side divided by the adjacent side, you will have dA by L. And the opposite side, you can write dA as v dt by L, and then you will replace v by L, which is du by dy, okay, and the dt. And you are looking for d beta by dt. Why? I have said for solid materials, d beta is enough. But for fluids, this d beta changes continuously. Therefore, instead of d beta, we are looking for d beta per dt. Okay. That is what Newton has told us. So at the end, Newton says that the applied for shear stress is proportional to, is equal to some constant multiplied with d beta by dt. Or instead of d beta by dt, you can write du by dy, which is very similar to Hooke's law. Hooke says that F is equal to k times delta x. F and del x is the response of the spring, that is the coefficient. Here, this is the force, that is the response of the fluid to that force, and this is the coefficient. That coefficient is called viscosity. Okay, and we have 10 minutes. I think we can finish after 10 minutes. So that is called viscosity. So what is viscosity now? So if applied shear stress is proportional to this shear strain, this one is strain rate, because the angle changes. If angle changes, it is strain, shear strain rate, actually not strain, shear strain rate. And this proportional to constant is called viscosity. Okay, so what is viscosity? So let me show you some examples on viscosity. So then you will understand what is viscosity. I have 3 spheres here. You can see one is dropped in biodiesel. First fluid is biodiesel. Second fluid is glycerin. And the third fluid is vegetable oil. And these are the spheres. You can see the spheres. We have the similar experiment in our laboratory. You can see the first one falls very suddenly, and the second one comes very slowly, and the third one comes in the medium range. You can see. So the question is why the first one comes very slow, fast, and the second one comes very slowly. And the reason is, we have said, let me see which color is best for this one. So the reason is the friction, because this is the sphere. Okay, when the sphere falls, the fluid is opposing the motion by shear force. Shear and the shear force. It is very similar to rubbing your palm. Rubbing palm. Okay, when you rub your palms of your hands, you can feel the friction between your palms. Okay, similar thing happens here. When the sphere tries to fall, the shear force from both sides prevent the motion, and here friction is more, and here friction is medium range, and here friction is the minimum. Okay, this force, this friction against the motion is called viscosity. Okay, what is viscosity? Viscosity is friction of fluid layers. Okay, and the fluid layers, I mean, you can say very similar to palms. Okay, fluid palms to motion. Okay, friction of fluid layers, this sphere tries to fall off, but the friction of the fluid layers prevent it, and that is what we call as the viscosity. And Newton has found that the shear stress that we apply here and the viscosity, shear stress is proportional to viscosity, which is shown by mu. This is the viscosity. Mu is proportional to du by dy, or mu d beta by dt. That is what we call as the viscosity. And this one is a linear relationship, linear. Okay, if it is linear, if the fluids have this linear relationship, these are called Newtonian fluids. Okay, if the fluids do not hold this relationship, they are called non-Newtonian fluids. Non-Newtonian fluids do not have mu du by dy. Instead, they have nu du by dy to the power of n. So here you don't have any linear proportionality. It is non-linear. Here it is proportional to du by dy with viscosity of mu, but here it is coefficient. Here it is proportional to the power of n, exponent n. And this here it is not called viscosity. It is called apparent viscosity. Okay, apparent viscosity, and here it is called viscosity, just viscosity. And the fluid mechanics one, in this fluid mechanics course, we are learning Newtonian fluids. What are the Newtonian fluids? Let's see it. Newtonian fluid is oil, Newtonian fluid is water, and the Newtonian fluid is air. Okay. So my question comes to you, and this will be the end of our. No, this will not be the end. We will have one more time. But the question comes to you, mu of these three fluids. Okay, you can leave as a comment. Okay, if you can leave as a comment, and the first 3%. Okay, first 3%. I will give marks to them. Okay, they will have extra grades due to this question. So these fluids, which one has higher viscosity? So you should say that, for example, mu oil is greater than mu water, and that is greater than mu air. Or you can say that mu water is greater than mu air, it is greater than mu water, mu oil. Okay, you should list this one and the reason. And the reason. This is my question to you, and you have 2 minutes, and let's see who will give the true answer. And at the end, you will get some marks to your activities during the semester. You can leave as a comment. But there are. Let's see who will give the true answer for the question. You should also say the reason. Okay, why? The reason is from the graph. Okay, you have a graph here. While looking at the graph, you should say this one is greater than that one, this one is greater than that one, and the reason. What is the reason? You can write the reason. because of shear stress. That is not the reason.
Density.
Sorry?
Density.
You can write as a comment, Ruslan. Let's see. Distance bigger. What do you mean by distance? Mu oil, mu water, mu air, that is large because of friction. No, you cannot understand the friction from this picture. Okay, this is graph. This is just a graph. You cannot understand it. You cannot understand the friction from this graph, but you can understand something. This is the Newton's law of viscosity. Tau is mu du dy. And this one is the tau, and this one is the rate of deformation. And you can, no, if you cannot drop a ball. Okay, so there are two answers. Water greater than oil, greater than air. Ruslan is wrong. Farid, let's see, mu oil, mu water, mu. Safar is true, yes. Oil, water, air. Reza is true, yes. Rajab, air, false. Farid, oil, water, false. There are two oil. Farid, there is two. Okay, the reason is, let me say, the answer is, you have finished your 2 minutes. The answer is the first oil, it has a higher viscosity than the water and than air. The reason is, you can understand it, this one is du dy, and this one is the tau. And we have said that tau is mu into du dy. And it is very similar to F is equal to Kx. What is K? K is slope. Okay. You can see that oil has the highest slope. Slope of oil is this one. Water has less slope, and the air has minimum slope. Okay, that is the reason of the range of viscosities. You are true that the friction of oil is more than friction of water. Friction of water is greater than friction of air. You are right, but the question is, from this graph, how can you say that oil is larger than water and air? And the answer is the slope. And you can see the slope of oil is something like this one. But if I choose another fluid, something like this one, this will have the maximum viscosity. And if I choose another fluid, something like this one, and this one will be the minimum viscosity. Okay, and one more reason, I can say you one more experiment. So if you move through water, okay, you can still feel the friction of the water, okay? Because when you move through the water, you can feel the resistance of water against you. But if you move through air, okay, if you move through air, you cannot feel the resistance of the air because air has less friction. It is all about not density, okay? I can give you, for example, mercury and the water. So mercury has density of, I think, 10 times more than, so this one is density of air. Density of mercury, water is 13 times more than water. But if you come to viscosity, viscosity of mercury is less than viscosity of water. Okay, you see, it is not dependent on the density. It is all molecular viewpoint. Okay, it is all about the molecular viewpoint, and therefore, if you say that density of air is less and therefore we can't feel the presence of air, that is false. It is all about the friction. It is all about viscosity. Okay, density is not a player here. And if you move, for example, through the car, if you move with the car and take your hand out of the window of the car, and you can feel the presence of air at that fast speeds. Okay, and if you change the orientation of your hand, if you put your hand against the air, or if you put hand in any different orientations, and you can feel the resistance of the air against you. And that resistance is what we call as viscosity, and what Newton called as viscosity. Okay, these are the Newtonian fluids. But life is not so easy always. Life is not so easy always because Newtonian fluids are not so common. Yes, the water, air, oil is everywhere, but we don't have Newtonian fluids everywhere. We also have non-Newtonian fluids. I will give one example of non-Newtonian fluids and finish today's lecture. One example of the non-Newtonian fluid is the toothpaste. And the non-Newtonian fluids are also classified in their are also classified as being on plastic, pseudo-plastic, dilatant. Okay, we'll talk about in our next lectures. But toothpaste is non-Newtonian fluid. If you ask why, so if you squeeze the toothpaste, if you squeeze it, you can feel that till some point the toothpaste doesn't flow. Okay, till some point the paste is always there, but after some amount of shear stress, the paste starts to flow. Okay, till that point the paste doesn't flow, but after some amount of force, the paste starts to flow. Okay. Now these are non-Newtonian fluids because they don't show any similar behavior with the Newtonian fluids. In Newtonian fluids, when you squeeze it or when you apply the force, it gives with a constant proportionality. F is kx or tau is mu du dy. But for non-Newtonian fluids, that's not the case. I've said the toothpaste is a famous example. If you apply the force till some point, the paste doesn't flow, but after some point, it starts to flow as a Newtonian fluid. But it is non-Newtonian fluid. Okay, this is the end of today's lecture. And tomorrow we will have one more lecture on fluid mechanics. And we have seen, yes, we are almost in the half of the slots. Okay, so see you tomorrow. If you have questions, you can leave as a comment. Otherwise, we finish today's lecture.